Now that we have a big picture view of the key components of a microgrid, let's take a closer look at some of the technologies currently being used to make them work. The key technologies that are used to power and manage microgrids can be organized into three broad categories. Generation assets, the technologies that create energy, including distributed generation systems, combined heat and power, or CHP systems, and renewable energy technologies. Energy storage technologies, the technologies that store the energy generated. And advanced controls, the systems that manage this energy and optimize microgrid performance. Let's look first at distributed generation systems. Distributed generation, also called distributed energy, on-site generation, or district or decentralized energy, refers to a variety of technologies that generate electricity at or near where it will be used. Conventional power stations such as coal-fired, gas, and nuclear-powered plants, as well as hydroelectric dams and large-scale solar power stations, are centralized and often require electric energy to be transmitted over long distances. By contrast, distributed generation systems are decentralized, modular, and more flexible technologies that are located close to the load they serve. Distributed generation may serve a single structure, such as a home or business, or it may be part of a microgrid and serve multiple facilities, for example at a major industrial facility, a military base, or a large college campus. Let's now take a closer look at 5 basic types of generators that are commonly used in distributed energy applications: reciprocating engines, gas turbines, microturbines, steam turbines, and fuel cells. Reciprocating internal combustion engines are a mature technology used for power generation, transportation, and many other purposes. They have a wide range of capacities from as little as 10 kilowatts to as much as 10 megawatts and beyond, and they can be grouped together to provide much higher outputs. As can be seen in the diagram, in a reciprocating engine generator, fuel is burned in the engine, which then drives a generator to create electricity and hot exhaust gases. The 3 main types of reciprocating engines are diesel, natural gas, and dual fuel. Of all the types of reciprocating engines, those powered by natural gas have the potential for lowest emissions. Reciprocating engines are widely used because they can provide incremental energy quickly and cost-effectively. They can cycle on and off multiple times, and because they are relatively compact, they are easier to site than gas turbines. They can be used as standalone systems to provide backup or primary power to individual facilities or infrastructure, or they can be integrated into a microgrid. Gas turbines are also a mature technology with high reliability and relatively low emissions. They are available in sizes ranging from approximately 1 to more than 300 megawatts and are used to meet a diverse array of power needs, including propulsion, aircraft, ships and trains, direct drives, pumps and compressors, and stationary electricity generation. For electricity generation, gas turbines operate somewhat like reciprocating engines in that they burn fuel to create mechanical power that then runs a generator to create electricity. The hot gases from the burnt fuel are exhausted. Because the electrical generation efficiency of gas turbines declines significantly as the load is decreased, gas turbines provide the best economic performance in applications where the system operates at or near full load and are most suitable for applications like hospitals, campuses, industrial facilities, data centers, etc. Microturbines are relatively small combustion turbines that use gaseous or liquid fuel to power a turbine and create electricity. Their mode of operation is much like larger gas turbines, but they are significantly smaller and serve a different market. Individual microturbines range in size from 30 to 330 kilowatts, not megawatts like other systems we have discussed, but they can be integrated into modular packages with capacities exceeding 1,000 kilowatts. Due to their relatively small size, they are targeted to the small industrial and commercial buildings market and are specifically designed to be compact, affordable, reliable, and simple to install. They also have low emissions and require no cooling. Steam turbines are a mature technology and have been used since the 1880s for electricity production. In fact, most of the electricity generated in the United States is produced by steam turbines integrated in central power plants. As can be seen in the diagram, steam turbine systems are configured a bit differently than reciprocating engine and turbine systems. Fuel is first burned in a boiler to heat water into high-pressure steam, which is then used to drive a turbine that generates electricity. Steam turbine generators come in a wide range of sizes and capacities and can make use of a very broad range of fuel types. They are typically found at industrial plants, commercial buildings with high thermal loads, and district heating sites. Fuel cells are a relatively new technology that use an electrochemical process to convert the chemical energy in a fuel to electricity and waste heat. In contrast to reciprocating engines, gas turbines, and steam generators, all of which are combustion-based technologies, fuel cells generate electricity without combusting the fuel, and the byproducts of electricity generation are typically only water and heat. They can be used for distributed generation and have several advantages as a source of electricity. They can operate at higher efficiencies than combustion engines and convert the chemical energy in the fuel to electrical energy with efficiencies of up to 60%. They also have lower emissions than combustion engines because hydrogen fuel cells emit only water, so there are no carbon dioxide emissions and no air pollutants at the point of operation. Fuel cells are also quiet during operation as they have fewer moving parts. Now let's take a look at the second category of generation assets, combined or co-generated heat and power, commonly referred to as CHP. A CHP system produces electricity and useful thermal energy, heat, from a single source of energy at the same time. In some ways, a CHP system is similar to a standard power plant that also generates electricity and heat. The difference is that a typical power plant uses the electricity but discards the heat, while a CHP system makes use of both the electricity and the heat. In order to take maximum advantage of the heat that they capture, CHP systems are typically located at or near the point of consumption. As the illustration shows, compared to a facility that uses grid electricity and an on-site boiler for heating, a CHP system produces both simultaneously, increasing overall system efficiency significantly, on average from 50% efficient to 75% efficient and sometimes even higher. Any CHP system begins with a prime mover technology that drives the entire system. The prime mover technologies are the same distributed generation systems that we have already introduced: reciprocating engines, gas turbines, microturbines, boiler and steam turbines, and fuel cells. The pie chart shown on the slide from the U.S. Department of Energy indicates the number of sites in the U.S. utilizing each of these systems as of December 31, 2016. Current trends indicate that the total number of sites and systems is poised to rise dramatically over the coming years. As the pie chart indicates, all of these systems can work in a CHP system, depending on specific conditions and overall goals. But each system also has specific characteristics that make them more or less suited for specific applications. So let's take a look at each of these systems in a bit more detail. Reciprocating engines, gas turbines, and microturbines all operate in much the same way when they are used in CHP systems. As can be seen in the bottom part of the diagram, a source of fuel fires the engine or turbine that then powers a generator that creates electricity, similar to any distributed generation application. The difference, as can be seen in the top part of the diagram, is that the waste heat exhausted by the engine or the turbine is captured or, quote, recovered, and then used to create steam or hot water. The creation of combined heat and power makes these systems significantly more cost efficient than standalone distributed generation systems alone, and they should be considered for any application where the steam or hot water created from the waste heat can be effectively utilized. For a bit more detail, let's revisit each of these three distributed generation technologies and take a quick look at how they fit in CHP systems. Reciprocating engines are very common in CHP systems, currently accounting for roughly half of the installed CHP systems in the U.S. In contrast to reciprocating engines that only generate electricity, in CHP systems, the hot gases exhausted by these engines are captured and used to create steam or hot water that can then be used for heating or even cooling through a technology called an absorption chiller, which we will discuss later. As illustrated in the diagram, just like in a car, internal combustion of the fuel-air mixture drives the pistons, which in turn drive the generator. At the same time, a heat exchanger pulls heat from the hot waste gases to generate hot water or steam. Common applications for reciprocating engine CHP systems include universities, hospitals, water treatment facilities, industrial facilities, commercial buildings, and multifamily dwellings. Gas turbines are currently used to power roughly 15% of the CHP systems in the U.S. For CHP applications, gas turbines typically have favorable economics in sizes greater than 5 megawatts. They are well suited for industrial and institutional CHP applications, because the high temperature gas that the turbines exhaust can either be used to generate high pressure steam or used directly for heating or drying. Gas turbines can be operated with a wide range of gas and liquid fuels, but for CHP, natural gas is currently the most common fuel. Microturbines are currently used to power roughly 9% of the CHP systems in the U.S. In CHP applications, thermal energy from the microturbine exhaust is recovered to produce either hot water or low-pressure steam, not the high-pressure steam produced by full-size gas turbines. The temperature of microturbine exhaust also allows for its effective use with absorption cooling that is driven either by low-pressure steam or by the exhaust heat directly. Common applications for microturbine CHP systems include hotels, nursing homes, health clubs, commercial buildings, food processing plants, and small manufacturing operations. Steam turbines are currently used to power roughly 15% of CHP systems in the U.S. As can be seen in the diagram, CHP systems that use steam turbines are configured differently than systems that use reciprocating engines or combustion-driven turbines. Instead of recovering waste heat from burnt fuel exhaust, steam systems recover low-pressure steam. Once recovered, this low-pressure steam is available to satisfy on-site thermal needs. As mentioned before, steam turbines burn fuel in a boiler to heat water into high-pressure steam, which is then used to drive a turbine that generates electricity and produces low-pressure steam as a byproduct. The boilers in these systems can utilize a wide range of fuels, including natural gas, oil, coal, or biomass. Steam turbines are typically designed to deliver relatively large amounts of thermal energy with electricity generated as a byproduct of heat generation. So CHP applications using a steam turbine will perform optimally if they can serve a large heating load, for example in a hospital, industrial facility, or campus with district heating. Overall system efficiencies in these situations can reach or exceed 80%. Fuel cells are currently used to power roughly 3% of CHP systems in the U.S. and are available with capacities from 5 to 2,800 kilowatts. As noted earlier, the main byproducts from fuel cell electricity production are water and heat. Fuel cell-driven CHP systems recover this relatively low-temperature waste heat and use it to generate hot water, low-pressure steam, or to drive absorption chillers. The majority of fuel cell CHP systems are used in commercial and institutional buildings, such as universities, hospitals, nursing homes, hotels, and office buildings, where there is a relatively high coincident demand for electricity and thermal energy. Over the course of this section of the curriculum, we have occasionally mentioned a technology that may be unfamiliar to some, absorption chillers. Because they can be very useful components in certain types of CHP applications, let's take a quick look at what they are and how they work, starting with the basic definition of a chiller. Chillers are used in commercial buildings and industrial plants to provide air conditioning, refrigeration, and process fluid cooling. There are two basic types of chillers, vapor compression and one called sorption. Vapor compression chillers are most often driven by electric motors. Sorption chillers, which are available in either absorption or adsorption designs, are driven by thermal energy, heat, using a thermal compressor instead of the mechanical compressor found in vapor compression chillers. Absorption chillers are often driven by thermal energy produced from a direct-fired burner, but they can also be driven by thermal energy recovered from combined heat and power systems, like reciprocating engines, gas turbines, microturbines, and fuel cells. They can use this heat directly to meet cooling loads and, as a consequence, need very little electricity compared to electric chillers. Absorption chillers provide a very viable option for using the thermal energy produced by a CHP system to create cooling. Now let's take a look at the third category of generation assets, renewable energy technologies. These technologies are often critically important components of successful microgrids, augmenting and balancing other power generation systems like distributed generators or CHP. In fact, most successful microgrids combine some form of relatively large, highly efficient system like CHP that is centrally located, with a suite of smaller renewable systems like photovoltaics that are more widely dispersed across the microgrid territory. A wide range of renewable technologies can be incorporated into microgrids. Solar thermal, where the sun heats hot water, biomass, where organic matter is used as fuel to generate electricity, hydropower, using the flow of water to generate electricity, and geothermal, tapping heat within the earth to generate power. While all four of these strategies are technically feasible and have been used in successful microgrids, The two most viable and common technology currently in use are photovoltaics and wind. Let's take a closer look at each of these technologies in a bit more detail. Photovoltaics, PV, allow the direct conversion of sunlight, photons, into electricity by a semiconductor. PV panels capture sunlight and transform it into DC power, which then enters an inverter to convert it to AC power. Solar PV generates electricity during the day, which is when facilities generally use the most electricity anyway. As a result, it can lower a facility's peak electricity demand. PV systems can be connected to the grid or completely off-grid, where they often include some type of battery storage. When used in microgrids, PV systems will connect to the microgrid, and the microgrid in turn will connect to the utility grid. The panels can be ground-mounted, roof-mounted, or incorporated into a carport or a canopy. Wind power continues to increase its share of electricity generation across the U.S., and the trend lines continue to be upward. In wind turbine systems, wind turns the blades, which then spin a shaft that connects to a generator to create electricity. Essentially, wind turbines convert kinetic energy in the wind into mechanical power, which is then converted to electricity. Wind turbines typically have 3 blades. If the wind resource is available, wind energy can provide cheap and renewable power. Utility-scale wind turbines range in size from 100 kilowatts to as large as several megawatts. Larger wind turbines are typically most cost-effective and can be grouped into wind farms. Wind turbines can form a part of the technology mix for a microgrid, depending on the size and location of the microgrid itself. Small-scale turbines typically serve small loads, like individual homes, and may not contribute much energy to a microgrid unless a large number of small turbines are fielded. Utility-scale turbines, on the other hand, provide significantly more electricity output, and if wind conditions are favorable, can be part of the technology mix for a successful microgrid. In addition to a mix of generation assets, microgrids are increasingly including some kind of energy storage, especially microgrids that include renewable energy resources such as wind and solar. Currently, a wide array of technologies and systems exist to store energy for a wide range of applications, including a large selection of batteries and battery technologies, flywheels that harness rotational energy to store and then redeploy electrical energy, compressed air energy storage, thermal systems that capture and store heat or cold for later use, and pumped water systems that use pumps to elevate water during off-peak times and release it to generate power during peak times. Current state of practice primarily uses batteries as the energy storage medium for microgrids. Controls are at the heart of a successful microgrid. Microgrid controllers are capable of automatically integrating and coordinating the generation, storage, if applicable, controllable loads, and the grid intertie equipment that allow a microgrid to interact with the larger grid as an aggregated single system. A microgrid controller includes the functions that define the microgrid as a system that can manage itself, operate autonomously or grid-connected, and seamlessly connect to and disconnect from the main distribution grid for the exchange of power and the supply of ancillary services. A microgrid controller should have both real-time control and energy management functions. Some of these functions may include grid-connected and islanded operation modes, automatic transition from grid-connected to islanded mode to provide uninterrupted power to microgrid loads during abnormal conditions, resynchronization and reconnection from islanded mode to grid-connected mode, energy management to optimize both real and reactive power generation and consumption, and ancillary services by participating in the energy market and/or utility system operations where cost-effective. And finally, no matter what mix of generation assets, renewable technologies, energy storage, and controls that is ultimately used in a microgrid, the performance of the system can be significantly improved by ensuring that the end users of the power, the loads, are as efficient as possible. Adding energy efficiency upgrades to the facilities connected to a microgrid will improve the overall performance of the system, reducing its costs and potentially enabling additional facilities to be connected. As a consequence, efficiency can almost be treated like an addition generation asset from the perspective of a microgrid's performance and cost effectiveness. The New Jersey Clean Energy Program has a wide range of programs and incentives designed explicitly to help improve the energy efficiency of facilities and businesses across the state, and should be consulted as part of any microgrid development process.